Here I'm going to give another example of using multiplexers for implementing logic. So this is a function. This is actually the same function as I've given in practice exercise 1C. And so here we have a 3-input function. And the easiest way to implement this is to use an 8-to-1 multiplexer that has log base 2 of 8, or 3 select lines. So there are select lines, select line 2, select line 1, and select line 0, select line 2 to 0. And here we put A, B, and C on our select lines. So the easiest way is to put, well, this is data input 0, 1, 2, 3, 4, 5, 6, and 7. You could also write those in binary, but it's faster to write it in decimal. And so now we can pull off the zeros. Here's a 0 and 1 combinations are 0. So our 4, 5, and 7, we tie those to ground. And here is our, and the remaining ones are 1s, so 2, 3, and 6. We tie those high. And then we don't forget to tie our output to W. So we can also use smaller multiplexers to implement this function. So for example, we could use a 4-to-1 multiplexer. A 4-to-1 multiplexer has log base 2 of 4 select lines, so it has 2 select lines. And so we can only choose 2 of our inputs to put on those select lines, either A and B, B and C, or A and C. So we can try them all out and see which one uses the fewest number of additional gates. So let's start with A and B. It's the easiest one to look at just because of the way the table is laid out. So we have 4 possible combinations of A and B. And now we can look at each of those combinations. So here is the 0, 0 combination when A and B are both 0. So when A and B are both 0, independent of what C does, the output is 0. When A and B are 0, 1, so there's our 0, 1 on A and B, the output is, well, 1, independent of C. When A and B are 1, 0, the output is 0, independent of C. And when A and B are 1, 1, well, now the output does the opposite of what C does. So when C is 0, W is 1. When C is 1, W is 0, in the case that A and B are both 1. So we put C bar in our output W. So when A and B are both 1, the output W does the opposite of what C does. So W equals C bar in that case. Okay, so in this implementation would need a single gate, would need an inverter to produce C bar from C. Okay, so let's now check out the other possibilities to see if they use fewer gates. So now instead of having A and B on the select lines, we could choose to have B and C on the select lines. So now we have the same possible combinations of that, 0, 0, 0, 1, 1, 0, and 1, 1, but now these are located in different places in our truth table. So the 0, 0, where B and C are both 0, are in those 2 rows. So the output W, when B and C are both 0, is 0 independent of what A does. When B and C are 0 and 1, those 2 rows, the output W is again 0 independent of what A does. So when B and C are 1, 0, the output is 1 independent of what A does. And finally, the last one, when B and C are both 1, the output is the opposite of A. So when A is 0, W is 1. When A is 1, W is 0. So we put A bar here. So again, for this implementation, if we put B and C on the select lines, we need a single inverter in addition to the multiplexer to implement this function. So now let's try the final combination is A and C on the select lines. So now if A and C are 0, those are those two rows. Look at the output, and the output follows B. When B is 0, W is 0. When B is 1, W is 1. Okay, so we put B in our output. We look at the next one. When A is 0 and C is 1, those two rows, well, again, it follows B. When B is 0, W is 0. When B is 1, W is 1. So our output, we put B there. When A and C are 1, 0, again, follows B. B is 0, output 0. B is 1, output is 1. And the final combination of A and C, A is 1 and C is 1 in those two rows. And the output is 0, independent of B. So this implementation doesn't require any additional logic gates. Doesn't require the additional inverter needed by these two implementations. So we'll choose that third implementation, and we can draw it here. Here's our 4-to-1 multiplexer. And here are our select lines. We can put select line 1 and select line 0. Select line 1 we're going to tie to A, select line 0 to C, and then we have our inputs to our multiplexer, 0, 1, 2, and 3. 0, 1, and 2 are tied to the input B, and input 3, the 1, 1 combination, is grounded. And then again, we don't forget to tie our output of our multiplexer to the actual output W. Now we can try an even smaller multiplexer implementation, and now we're going to use a 2-to-1 multiplexer. And so now we can just choose a single input, A or B or C, to put on the select line. So we can try, kind of any combination. So let's start with A. For A, choosing A for the input to put on the select line, we could look at either of these kind of minimized truth tables. And so, or reduced truth tables. So now our possible values for A are 0 and 1. So when A is 0, these two rows, well, the output just follows B. B is 0, W is 0, B is 1, W is 1. All right? And now, when A is 1, well, the only way we're going to get a 1 on our output, we won't get a 1 when B is 0, but we could get a 1 when B is 1 and C is 0. So B and C bar. And we could have gotten that same result from this table here. Let's go ahead and take a look at that one. A, W will do the same process that we just did. When A is 0, well, the output is just B, independent of what C does. When A is 1, well, these two rows, the only way we're going to get a 1 on that output is if C is low and B is high. So C bar B, or in other words, B C bar. Okay, so we could have gotten that kind of reduced truth table using either that starting truth table or this one. Get the same result. Okay, so now we could try what happens if we put B on the select line. So we can use either of these two tables to get that result. We'll start with this table. So when B is 0, these two rows, there's no way to get a 1 on our output W, so the output is just 0, independent of C. And next case, when B is 1, well, we can get a 1 if C is 0. So if C is 0, we're going to get a 1. Or if C is 1 and A is low. Okay, cool. And now we write, if it helps you, you can also write this as C bar and 1, which ends up just to be C bar, or C and A bar. So now we're going to take that and realize that we can do some Boolean algebra on that using the simplification theorem. We're going to get C bar or A bar. Cool. We can also recognize that as, oh, hey, that's just write it as alphabetical order. That is just the NAND function using De Morgan's. Okay, so that one requires just a single gate. This one requires two gates, an AND gate and an inverter. So if these were our only choices, we would definitely choose this one because it requires just a single gate, an AND gate. So we could have gotten the same result from this table. Let's just do that for example. So we have B again on our select line, 0 and 1. So B is 0 in this row and this row. So independent of A, the output's going to be 0. And then B is 1 in that row and that row. So the way we could get a 1 is if B is 1, we're going to get a 1. Or I mean, if A is 0. So the way we can get a 1 is if A is 0. So A bar and 1, if you want to do it that way, A bar. Or A is 1 and C is low, and C bar. A and C bar. Again, using simplification theorem, we're going to get equals A bar or C bar. And again, we can recognize that using De Morgan's as the NAND function. Okay, so of these two options, the second option, having B on the select line, is better. Let's try the last option, which is having C on our select line, just for good measure. So if we have C on our select line, again, there's two options. We can look over here. If C on the select line, C is 0 in these two rows, well, the output's B, independent of A. Now we have C is 1 in these two rows. Well, the way we can get a 1 is if A is low and B is high. So A bar, B. When A is high, there's no way to get a 1 on our output W. Okay, so again, this one requires an inverter and an AND gate. So this one, having B on our select line, is the winner here. So we put B on our select line, 0, 1, our output W. 0, we're going to tie to 0. I can also write the logical 0 instead of the ground symbol. Either works. And here we have our NAND gate, our single gate, tied to A and C. We could also reduce it even further. So here's an example of reducing it further. 0, 1, we have 0, A bar, or C bar. Again, that's equal to A and C, all of that bar, using De Morgan's. Remember that this A bar, C bar is not equal to A and C, all of it bar. In fact, A bar and C bar is equal to A or C, all of that bar, using De Morgan's, but not equal to A and C, all of the bar. Okay, so here we have our reduced truth table, and I want to reduce it again. Well, really that's just putting it into logic gates instead of using a multiplexer. The only way we're going to get an output of 1 on W is in the case that B is 1. We're going to get B, and, so B is true, and this expression is true. A bar or C bar, we end up with B, A bar, or B, C bar. Or in alphabetical order, A bar B, or B, C bar. And so we've reduced it kind of repeatedly until we got back to our gates, our gate level form of the function. And we could have read that same equation from the other reduced truth tables that we had. So here's the one where we had A on the select line, which we didn't use because it required 2 gates instead of 1. But here we would write W is equal to, well, the way we can get a 1 on our output W is if A is false and B is true, A bar B, or if A is true and this term is true. Okay, that looks a little bit different from what we had before, but now we can use Boolean algebra, K-maps, etc., all the tools that we have now to reduce that. In this case, Boolean algebra is possibly the easiest, and so we can basically look at this and say, oh, that's covering a term that I could use to reduce this term. So A bar B, or A bar B and something. Well, I need everything else to be the same, so A is already different, so C bar goes there. Bring down our other term. Now combine these two, and we get, well, A bar B, that one comes down, and we combine those last two, or B and C bar, and we get that same expression. And we get that same expression that we did in the prior slide. So we can also read expressions off of our multiplexer. So our output Y will be true, well, if A is 0, so A bar, and what's coming into it is also true. So and B and C. Or, the other case, if A is true. Well, if A is true and what's coming into it is true, well, we already always know that that's true because that's a high input. So we put A and 1 if you want. But that's also just A. And now we can take this equation and see if we can reduce it. In fact, we can. We have A bar, B, C, or A. Using simplification theorem, we can get rid of that A bar. So we're going to get B and C or A. I'll also write that as A or B, C. Either way works. So we can also go the other direction where we start with the multiplexer implementation and then write the function that it implements.